Okay, so last time we were talking about the SYK model, and we discussed how to go from the original model with the fermionic variables to a reformulation of the model where we write it in terms of a path integral over variables g and sigma, where n appears as a coupling constant. And we had started to discuss how to do some computations there, and we discussed how to compute the leading order terms in the free energy, which came simply from doing this path integral and evaluating it by replacing the classical solution in the path integral. And that way we get the leading order approximation to the free energy. Now we can similarly consider a 4-point function. So here we have a 4-point function where we have fermions at times. So the arguments here are the times at which the fermions are evaluated. Here there is no sum over these indices. I mean, you can put a sum and divide by n if you wish. And this expression is given by doing the path integral with an insertion of this basic variable. So the 4-point function of the fermions is like a 2-point function of these bilocal fields. Okay? So here we are supposed to do a functional integral with these bilocal fields, and if we did the functional integral, we would get the expression for the fermions, for the fermion correlators, and the leading order expression for those correlators would come from taking the classical solution that we have for the action. We replace it in the action, and then here we also replace it here, so that we just simply get the classical solution, and that is just given by the leading order expression for the fermion 2-point function, and we get something which looks like a disconnected correlator. So it's just simply the correlator of the two fermions times the correlator of the other two fermions. Now, in this approximation that we are working with, the model has an ON symmetry, and so fermions with different indices have no direct correlators. And then we could do this path integral to the next order. So we could take the action and expand the action around the classical action, plus some small fluctuations, both in g and sigma, which will be of quadratic order. And then we have some kernel here, which is roughly like a kinetic term for these fluctuations. And by integrating out those fluctuations, we'll get some answer, which will go like 1 over n. That comes from this n here. And we get some expression which now will link the two variables. It's like the propagator for this field. So it's like the inverse of this kinetic term that we have here. We'll get that inverse here, and that will be the connected 2-point function. So that's all standard as in any field theory. The only and everything that I've said so far since I started the lecture is valid for any energies, so for any values of the times, and is valid to in an expansion in n. So now this action is a little complicated, and it might be difficult to invert this kernel, and you can do it numerically, and you can find numerically these values. Yes, please. Yes, sure. From now on, I'll try to write larger. Please remind me, I forget. I see it large here. Okay, so everything that I said is valid for any energies, but now when you go to low energies, special things happen. First of all, it becomes simpler to solve the equations. We discussed that at low energies, the solution for these equations are simply powers of the times, so they have a scale invariant form. And well, we could also go to the finite temperature by the map we discussed before, and we had some signs here. And also this kernel simplifies, and one can use conformal methods to invert it. So there is some method to invert this kernel. But as we discussed and in principle, if one looks at it naively, one can write down a formal expression for the inversion of this kernel. But when one is a little more careful, one realizes that one cannot really invert that kernel because there are some zero modes. And the zero modes of the conformal kernel come from the fact that we had this reparametrization symmetry. Remember that we discussed that? Yes?
So this one is valid of Euclidean and Lorentzian sum?
Yes, yes, yes. Everything that I said is valid in both cases. And yeah, so we cannot first take the low energy limit and then invert this kernel because the kernel has no inverse. So in order to do that, we need to remember that there is a particular mode, which was this reparametrization mode that had zero action in the low energy theory, but when we go to the full theory, it has a non-trivial action. And so that mode was parametrized by the Schwartzian variable, so we can we can imagine this as being some, let's say, perpendicular variables, let me call them. Those are perpendicular to the Schwartzian variable. So those have a perfectly fine kernel, and we can deal with it with conformal methods. And then there will be here a term of the form alpha n over j, and then here the Schwartzian action. Sorry, Nati, but as a function. So we have this term, and that here at low energies, this factor will be very small, and that implies that when we invert this, we get a big factor here in the correlator. So the leading expression, the leading terms in the correlator will come from integrating this variable. So those are the biggest, numerically the biggest parts of the correlator. And so at low energies, so if we, for example, do the Euclidean, well, at low energies, we'll have a piece that is enhanced by a factor of, let's say, beta j, or this could be some time scale, so some time scale, for example, beta. And then we'll have some function of, let's say, the ratios of times over beta, for example, of all the individual times that will come from inverting this term in the action. And then we'll have some other piece which will be independent of beta j that will come from this other term in the Lagrangian. So now I'd like to discuss a little bit how to compute these enhanced terms that come purely from this action. So for that, we can imagine that we are computing this 4-point function, and we can imagine we do a change of variables from those variables g and sigma to integrating over the perpendicular variables, and then the functions for the variables for f. So we are going to write this as the integral over all f's, and we have to divide here by the volume of SL2. As we said, we had an SL2 gauge symmetry, so we add these things. And then here we'll put the g, so these functions, but transformed with f. So this is just f prime 1, f prime 2 over f1 minus f2. So this is explicitly what it is, to the 2 delta. So this is just taking this function and transforming it by f. And then we have the same thing here for 3 and 4. And we get here the Schwartzian action, alpha n over j times the Schwartzian of f and let's say t. So t is the physical time, and I'm going, in the rest of the lecture, I'm going to call it u, just not to confuse it with some other time variables. So u is the physical time of the theory. And we can think of f as an infrared time, and this picture will become a little more clear when we talk about ADS2. But for now on, from now, we just have this action. And so this is the action, this is the part of the path integral that corresponds to integrating over the f mode. So recall that we had this picture of the space of over which we are integrating, the space of g's and sigmas. This is a high-dimensional space. We had one classical solution, and then we had a valley with very low action, and then some perpendicular directions. So we could imagine that we, let's say, first integrate out the perpendicular directions, and now we are doing an integral along the valley. And we have a shallow action along the valley, and this is the shallow action that we have. And so, good. And in this way, one can compute it. I will not discuss in great detail the computations, but so this determines one piece of the correlator, and this piece of the correlator also contains in it the growth of the you can compute from this the out-of-time order correlator, and it will contain the an exponentially growing term with the maximal chaos exponent. Okay, and I'll give you a slightly more physical, slightly different explanation in the context of ADS2 why we get that that exponent. But for now, you can that calculation simply corresponds to taking the leading order. So now we can take this action, and even in this action we can expand to leading order in 1 over n. So we replace first the classical solution for f, which could be that tangent hyperbolic we discussed, and then we expand around it. And in that way, we get that 4-point function we were talking about. So I'm only going to quote the final answer, and the explanation for that final answer will be more clear once we introduce the ADS2 discussion. So this 4-point function divided by the 2-point function, sort of the out-of-time order correlator, will have the form 1 minus beta j over n times this e to the 2 pi t over beta, right? So the growing term that Douglas discussed. And so the exponential time dependence is fixed by the group theory structure of this action. And again, this will become more clear in the rest of the lecture. But what I wanted to emphasize is the fact that it comes purely from this term in the action.
Will be u, the physical time? Or?
Yes, sorry. Yes, yes. And there are several other properties that are determined by the Schwartzian action. We'll see perhaps tomorrow that is related to some phenomenon of quantum teleportation in the thermofield double state, and we'll discuss that in detail. And there are some other, there are several other physical phenomena that are governed by this action. And we discussed one last time, which was the near extremal entropy. Okay. So before I tell you exactly how to get this result, I'll like to discuss a bit ADS2, so that this is something that remained from last lecture. And now I'm going to start discussing ADS2. But before I discuss ADS2, I'd like to discuss a little bit some general remarks about decoupling limits. So in general, we are interested in black holes. And so we have a black hole. And we look at the black hole from outside, and we are interested in asking questions about this black hole. So we are interested in saying, well, we send some information into the black hole and watch what comes out and so on. And we imagine the black hole has some Hilbert space, so the Hilbert space of the black hole. And we'll have operators acting on this Hilbert space. But if we have a black hole that is interacting with the outside, of course, we have also some fields outside. Let's say phi, some field that lives outside. And there will be couplings between the operators. Let's say this is the Hilbert space of the black hole. And then we have some coupling, some operator that couples to phi. So there are some operators, some couplings in the Lagrangian that involve the operator times phi and the black hole Hilbert space. Now, and in general, this, the mere fact that we are coupling it to the outside also leads to corrections to the dynamics of the black hole itself, because we could have the same operator and close the loop this way. It induces extra terms in the Lagrangian. So the actual precise dynamics depends on how we couple it to the outside. So it's sometimes useful to somehow decouple as much as possible the black hole from the outside. And So one way that one can do this somewhat is to consider, let's say, the flat space. We have a black hole in flat space, and we consider certain limits of black holes. So in particular, a limit that is useful for thinking about this is the near extremal limit. So we can think of a charged black hole that carries some charge q. And those black holes have to have masses which are bigger or equal than q by cosmic censorship. And when the mass approaches q, then the black hole develops a very long throat with an ADS2 in 4 dimensions, an ADS2 times S2 near horizon geometry, an ADS2 throat. And then there is a horizon here deeper inside the throat. That's the picture for a near extremal black hole. And so in these cases, we have this long throat, and we can try to imagine decoupling this whole throat from the rest of the space. And of course, this is a method that works very nicely in higher dimensional ADS spaces and leads to the decoupling limit that relates conformal field theories to ADS spaces. But let's try to understand how that decoupling limit works in this case. So the most naive idea would be to say that it also works in this case, and that we should have and there should be some version of ADS2 CFT1. So if you don't remember anything else from this lecture, I want to remember that this is wrong. Okay. But it's not completely wrong. So the idea is that the decoupling limit works differently in this case, and we have something which we will call nearly ADS2, nearly CFT1. And an example of a nearly CFT1 is the SYK model at low energies that is almost conformal, but the conformal symmetry is broken by a term like this in the Lagrangian. Okay, so
rather than say that the first one is wrong, would you not want to say that it only describes the extremal entropy? Or maybe
yes. So I'll yes, one could, yeah. Let me. Well, I think it's wrong in spirit, and because.
Well, I guess for the SYK model, there's no true extremal entropy.
No, well, the thing is that something that you could say is ADS2 TFT1, topological field theory. Even the one is a little dubious because it's just there is no time. Okay, so that makes sense, and that describes the BPS states. And in this sense, yeah. So in this case, so if you have, this is a general comment, which is that if you have a conformal scale invariant system, then you can ask what the density of states is for that scale invariant system in 1 dimension. And 2 possible answers for the density of state that are scale invariant are delta of E. So it has to have density of states has dimensions of 1 over energy. So this is one possibility. And another possibility could be 1 over E. Okay. Now, if the density of states is just delta of E, then we just have only the ground states. And we have no dynamics. Okay. Yes, please.
In this case, what goes wrong when you look at some brains and try to decouple them?
If by the end of the lecture it's not clear, I'll ask the question again. And so here what we are trying to see is that imagine the relationship was true, and we're trying to guess what the density of states of that dual quantum mechanical theory would be, right? So you could have a term like this, and that would describe only ground states, so all the completely degenerate states. Or you could have a term like this. And in this case, the integral over energies would diverge for very low energies. And very low energies are precisely the energies where we expect to have the conformal symmetry. And so we see that we get an inconsistency with the idea that a black hole should have a finite number of states, because those black holes have a finite area, there is an S2, and the extremal entropy is the area of that S2. And so we have some inconsistency. So this shows that we cannot have a system that has non-trivial dynamics. Because when we say CFT1, we're imagining something where the correlator would be a power of time, right? The correlator between two times would be a power of time. Yes?
Isn't the fact that it's continuous already a problem from that perspective, never mind the divergence of the integral at e equals 0?
Yes, yes, yes. That's already that is a problem. Yeah, what Douglas is remarking on is that if we had any continuous density of states, it's already a problem for a system that has a finite number of degrees of freedom, because a finite entropy, because we should have just a bunch of delta functions and not a continuous distribution. Okay. Okay, so of course you could just restrict to the extremal limit. There is nothing wrong about the extremal limit, and this is a wonderful subject that we are learning about at Tisch double-cars lectures, and you can do lots of wonderful things there. But if we ask about questions that involve dynamics, we need some better understanding. And the better understanding is the idea that we'll have to include some effects that break the conformal symmetry. Okay. So we already checked that it's not possible to have a conformal, a scale invariant system. Okay. Now, in order to understand the form of this breaking, let's continue with purely ADS2. So let's look at ADS2. ADS2, we can write down a metric which is, let's say, dc squared, ds squared equal to dc squared over c squared plus dt squared. So this is in Euclidean space. So this is Euclidean ADS2, or the hyperbolic plane. So that's the metric. Of course, you can also write the metric in terms of a disk. We sometimes even plot it this way. So we have ADS2. Has the picture of the hyperbolic disk. And this is a space that, if we have asymptotic boundary conditions, where we say that the metric looks locally like this, then we have some symmetries in those boundary conditions that come from, for example, taking t going to, which I can change t to some, let me write bigger. So asymptotic symmetries. So we can take t to be a function of time, and c to be f prime of t times a new variable c. And if you replace this in the previous metric, you find that, well, you get an f prime from here, and we cancel that with this c. And so the leading terms in the 1 over c expansion are invariant. Okay? Then there are some subleading terms that are not invariant. So this is only an asymptotic symmetry transformation, but it's not an isometry. Okay? So the only isometries of this metric are just SL2. So there is an SL2 group of isometries of transformations. So if f is restricted to an SL2 transformation, it leaves the metric invariant. But these more general transformations do not leave the metric invariant. Now, one way to understand what those do is the following. So we can imagine we have ADS2, and we put some boundary conditions far away where the metric is very large. Then we do one of these transformations. That will change the coordinates in the interior. And we can then reinstate the original coordinates. And if we put the same boundary conditions in the final coordinates that we're putting in the initial coordinates, that's the same as saying that we have the original space, and we are changing where we are putting the boundary conditions. So we are having really a physical change in the metric that came from this shift in the boundary conditions. And so these two geometries are locally the same, but the full geometry is different. So we have a whole family of inequivalent geometries when we do that. Okay. So for example, the one boundary condition we can imagine choosing is to say that the proper time along the boundary is just constant, is let's say the u squared over epsilon squared. So u is the proper time along the boundary, and that's what this u is what we're going to identify as the boundary coordinate. And if we looked at the classical action for ADS2, the naive action is would be just simply the Einstein term, and we of course have to add the boundary term. So this is over M2. This is the boundary of this M2. So M2 is this manifold. And then there is some overall coefficient that if we are coming from higher dimensions would be the area, the extremal value for the area. But we are going to generically call it phi 0. So this is what gives the black hole its entropy up to some factors of 2 pi. So this is an action which is topologically invariant and will give the same answer for this configuration and that configuration. Okay, so that's the naive low energy action. Now, yes, indeed. That's because this term is needed to cancel when we integrate by parts here. Okay. What do I need to say now? Okay, there's one more thing I should say, which is imagine we had quantum fields living on this geometry, right? Then if we have this other geometry, the value of the partition function for those quantum fields would be different in these two geometries if this new curve was at some finite location. But when we take it all the way to infinity, we get the same values, even if we had quantum fields. So this is really a symmetry of the field theory in ADS. I mean, that's related to the fact that this is an asymptotic symmetry. We get the same answer. And okay, so it's useful for continuing to analyze this problem to parameterize these curves in some useful way. And the following is a useful parameterization of these curves. So we can parameterize it by giving the value of, let's say we want to parameterize a curve in this metric. We could give c as a function of t, but instead what we're going to do is we're going to give t as a function of proper time and c as a function of the proper time, right? Since we're going to identify the proper time as the boundary time, this is something convenient. But we want to impose the boundary condition that we said over there. And for small c, the boundary condition looks like ds, essentially like dt over c. We can neglect the second term because it will be less important for small c. And then putting this parameterization and demanding that this goes like du over epsilon implies that, so these boundary conditions imply that c prime is equal to epsilon, c is equal to f prime u. Okay. So in the end of the day, we express the shape of the curve as some f of u, and that is a way simply to parameterize a curve.
What's its f?
F is f is t of u. We parameterize it in terms of a single function of u. So that's a totally simple way to parameterize the curve. Now, we had that term in the action, and we can say, well, what's the minimal modification to the action that we can have that will reflect the fact that the boundary conditions are not, we want to break slightly the SL2 symmetry. this reparametrization symmetry. And one way to break it with a local term would be to add simply an extrinsic curvature term. We'll later see how to get this from some more concrete actions. But let's say that this is a term we could imagine adding to the action that reflects a slight breaking of this asymptotic symmetry. And we can check that this indeed breaks the symmetry because we can compute it for this curve and find that this has the form of du over epsilon times 1 plus epsilon squared, and then the Schwartzian of t and u. Okay. This simply comes from calculating the extrinsic curvature. And then we can look at this and say, well, for small epsilon, this term diverges, but this divergence is just proportional to the proper length of the boundary. And we are always imagining we could subtract the divergence, which is proportional to the total length of the boundary. And then if we wanted to keep this as a finite term, then we can multiply this term by 1 over epsilon with some constant. And then we'll end up to this diversion term. We get an action which is that constant times the Schwartzian action for. Okay. So this is just a simple way to break that symmetry. And what we need, the only assumptions we need is that the effects that break the symmetry are relatively local in U. Notice that we're very close to the boundary, so a small time in U could be many ADS units near the boundary. So we need, this notion of locality is very lax. So it might be valid for a theory which is highly non-local in the bulk, like a string theory with a very low string tension. We could still have some local effects in this sense. Okay. Now, one important point is, as we also remarked in the SYK model, is that we have, when we look at those geometries, well, actually, we have those geometries over there. If we were to take, let's say, one of these geometries like M2 and move it in ADS2, so move it rigidly within ADS2, we would get the same cutout geometry. So the piece of the geometry we have inside is always the same. So that implies that functions that differ by an overall SL2 transformation are equivalent. So they're completely equivalent. And so in fact, this action, as the same as the SYK, has an SL2 gauge symmetry or redundancy, gauge redundancy, which comes from moving the whole picture inside the ambient ADS2 space. Okay.
So this cancels in the action you've already written. So the proposal is to add another given Sonic term with a different coefficient.
Yes. So we only have this term. We'll later show an action that only has this term. I'm here just pulling this out of a hat and saying this is a simple local action we could write down, and it could come from some effects which are local near the boundary. So the effects local near the boundary could be something proportional to the length, but this is not interesting. And then the next term we could write is something proportional to the extrinsic curvature. And this requires very minimal locality. It's just locality in U. It has little to do with locality in ADS. Okay?
Yeah.
That's
But usually we say the coefficient of k is fixed in the given Sonic.
well, we should have that term. We have that term, and in addition, we have this. This is an additional term that we have.
So I thought you needed to add the phi to make this consistent.
No, this is a consistent action as it is, and we'll later show that it is equivalent to the action with the phi. I motivated this way because this is more general than the derivation coming from the Akib title point that we'll later see. And I tried first to give you a very general symmetry-based argument, which has a range of validity bigger than the one we'll later, more explicit one that we'll talk about later. Another point is that this action is not invariant under rescalings of U. Okay. So if you change, let's say, U to lambda U, then this action contains ratios of derivatives of u, which has a net number of 2 derivatives of u, and is not invariant under rescalings of u, right? Well, I don't know if you remember the Schwartzian, but there were some terms that look like t double prime over t prime squared, right? This has a net number of 2 derivatives with respect to u, and if we do that rescaling, we'll get some non-cancellation of the lambda. So this action breaks the physical SL2 invariance. So the model is not SL2 invariant. It's not invariant under SL2, physical SL2 transformations or even scaling transformations. And that's good for solving the problem we had over there. Okay. But there are still many consequences of this pattern of symmetry breaking. And I wanted to emphasize the similarity between what we have here and the SYK discussion. So there, we also had a reparametrization symmetry. And let me make a little bit of an equivalence to what we had in the SYK. So in SYK, we had to lead in order a G conformal that went like 1 over T1 minus T2. And this is roughly the same in ADS2 as having the metric, the ADS2 geometry. So the ADS2 metric that is invariant under the SL2 transformation, exactly invariant. Then we had the reparametrization symmetry, which we also displayed clearly here as an asymptotic symmetry of ADS2. And at the level of just purely the conformal answer, this symmetry was spontaneously broken by the choice of either this G or the choice of the ADS2 metric. So we had a spontaneous breaking of this symmetry. And then in addition, we have also some explicit breaking. And that came from the UV dynamics here in the SYK model. And in ADS2, it comes from the fact that we cannot take the infinite decoupling limit, but we have to remember that this joins into some bigger space. And we have to keep the leading order effects that join this to the higher dimensional space. Okay? So when we look at the area here, so the area of the transverse sphere will be some extremal area plus some small change, and we need to keep into account this small change. And we'll now see how to do that. Okay, so this points out the similarities between the two cases and why this is the. So these two theories are in the same, let's say, universality class in what respects to the pattern of symmetries, symmetry breaking. Well, Douglas really mastered this, but. Okay, so now we are going to make a slight detour. We are going to start discussing these two-dimensional gravity theories. So what do we know about two-dimensional gravity theories? We're interested in this because we are trying to find the general reduction of this system where we have some internal manifold and then some two-dimensional gravity situation. And what I'm going to say now is very general for any case that, let's say, any spherical reduction of gravity to 2 dimensions. So even before we start, let me ask you whether we expect any propagating modes. Have you ever heard of spherical gravity waves? No. Yeah, so even before we start, we should find that whatever gravity actions we write, they should have no propagating modes. So this should not come as a surprise. It should be a physical requirement. Right? Now, the general two-dimensional reduction can be written. So there is some two-dimensional Einstein term, and in general, there could be some arbitrary function of some scalar field that has to do with the size of the internal dimensions, in this case, that area, or the size of the area of the sphere. We could have a term involving gradients of this field with, in general, some arbitrary function here, g of phi tilde. and we could have some general potential V of phi tilde. Okay? So those are the general terms we can write down. And we can, by a field redefinition, so we can redefine this to be, let's say, some phi. And then we can redefine the metric. Let me call tilde the metric that appeared in the original Lagrangian. We can define some function, let's say, h of phi times g mu nu. And in the end, this action becomes field redefinition equivalent to an action that contains just phi r plus u of phi. So this is the most general two-dimensional gravity action. And we can analyze any problem with this. It's sometimes called dilaton gravity for historical reasons. I think it's a very bad name. It should be called entropion gravity, because the name will not stick, unfortunately. But because this, why am I saying it should be called entropion gravity? Is because the value of phi at the horizon gives us the entropy, and this gravity theory encodes basically the thermodynamics of the system. So, in fact, any solution of this action, just purely this action without any matter, will have a Killing vector, which is given by epsilon mu nu d nu of phi. And so any solution of the action has a U1 symmetry. And Euclidean space, then we think that we have a black hole, Euclidean black hole with a U1 symmetry. And it's describing a thermodynamic situation. So once we fix some boundary conditions, let's say phi equal to phi b, we can calculate the value of the Euclidean action. And that will give us the thermodynamics of this black hole. And we can encode any thermodynamics we like by choosing the U of phi. Okay? So this action is quite similar in spirit to the action we wrote in a discussion session where we were talking about a hydrodynamic action for arbitrary. It's similar in spirit. But now, okay. So what are the simplest choices for U? The simplest choice is to say that U is constant, for example. And if you choose U to be constant, then that describes the near horizon geometry of an arbitrary black hole. And this is equivalent to some dilaton gravity theory that was studied in the 90s. That's not what we're going to do now. We're going to choose the next simplest choice, which is U equal to phi. Okay? So we're going to study the action integral of phi r plus 2. Here I've just adjusted the constant. Just by rescaling of the metric, we can adjust the constant in this way. And then, of course, we need to add the extrinsic curvature term. And then we have some phi b here, which is the boundary value of this phi. And in addition to these terms, we can also have the topological action that we haven't written, that we have erased, which is phi 0, the integral of square root of gr plus 2k. So this term will give us the extremal entropy, and now we'll try to concentrate on this one. This is just topological. This will not be totally topological. Okay. Now, the point is that this type of action is going to be describing the general situation of a near extremal black hole. And the reason is essentially that when you have a near extremal black hole, you have some extremal area, so the extremal value of the area. And if you naively take that to be the value of the area, you would get this type of action from the Einstein, from a Kaluza-Klein reduction. But if you remember that there is some small fluctuation of the area, because this eventually will connect to overall flat space, then you would include also this term, where phi should be viewed as a small fluctuation of the area. So we should think of the extremal area as phi naught, and this as being the phi that appear in this formula. Okay? Yes, please.
This might be a stupid question, but how do we keep the Kaluza-Klein modes from infecting the physics?
Yes. Yes, I'm going to address that. Now, something important is that when we imagine cutting this off, we're going to cut it off at some particular value of r, right? Some particular value of the size of the sphere, and that's some particular area. So that's why we are saying that the proper boundary conditions for this action correspond to fixing the value of phi b, right? That's physically telling us where we are going to patch this into flat space. Okay, Kaluza-Klein modes. So the Kaluza-Klein modes are other fields that will propagate on this geometry. They will be massive. They have a mass of order the radius of ADS, and we should include them, and they should be there in the physics. And in fact, the full action for our problem will be the topological action, let's say S0, the bottom term there, then S Jakob Teitelbaum, which is these two terms here, S Jakob Teitelbaum, and this is what we are calling S0. And in addition, we have some matter terms, S matter, that will be describing some fields moving in the geometry. So chi are some other fields that this could be Kaluza-Klein modes, for example. Here I have assumed that they don't couple to phi. And the reason for ignoring this is that when we look at the dynamics of the Kaluza-Klein modes, they will be moving on a space whose area is given by this, and the leading term is this term, and this is a small correction. So up to small corrections, we can ignore the coupling to phi. At next orders, we will include it. And the problem where we ignore the coupling to phi is actually rather simple, and that's what we are going to study now. And what I've tried to explain is why this simple problem makes physical sense for a near extremal black hole. I should also have emphasized that if you have a rotating black hole, you also can have an extremal limit. And we have rotating black holes in nature, and some are somewhat close to the extremal limit. So these are some of the black holes that exist. We would like to understand them. They also develop this critical regime where a nearly ADS2 geometry. Okay. Now let's study this action. So now, for the moment, we'll set the matter to 0, and we start studying this action. The equations of motion are, the equation of motion for phi is just simply setting r is equal to -2. So that sets the metric to ADS2. The equation of motion for the metric sets a bunch of derivatives plus some other terms equal to 0. And this is a bunch of constraints on phi. And so there are no propagating modes, because this is not the form of the wave equation. These are 3 equations as opposed to 1 equation. Very good. So this point that this is the general action we expect for any near extremal black hole was made by Almeri and Polchinski. Okay. Now, Lorentzian picture. Yes.
Almeri and Kant. The statement about this action coming from a general black hole is
Yeah.
by Almeri and Kant. You don't move Kant.
Okay, sorry. Thank you. Okay, so now we discussed that in the Euclidean case we could have all these various geometries, but then we have that action, and the only solution to that action is a geom up to overall translations, SL2 translations, is a simple circle. Okay. When we continue this to Lorentzian signature, we get a space, a geometry, where the boundary, so this should be symmetric, the boundary is, so this is the standard Lorentzian continuation, the thermophile double, my very favorite state. And This should be compared to the Penrose diagram of a 4-dimensional Dryson-Nostrom black hole, which has this form. So here is the asymptotically flat space. This is the horizon. Then there are some inner horizons. So this is the outer horizon. Then there are some inner horizons. And there are some singularities, which in this black hole are time-like. And there is a similar structure to the past. And the structure repeats infinitely to the future. So that's the Penrose diagram of the near extremal black hole. Now there's a whole discussion of whether we should trust or not trust the futures. I'm going to be agnostic, the future geometry here. If you have small perturbations, there tends to be a singularity at the inner Cauchy horizon that might make it access to these other regions difficult. But I think we should keep in mind that there might be other regions there that might be important. Now, how does this fit into here? So this is describing only the near horizon region. So this line here corresponds to some line here. And we are cutting off the space here and then patching it to flat space. That's what we were. That's the dotted line there that connects the throat to the rest of flat space. But we still get something analogous to these singularities in the following sense. So if we look at the solution for phi, so we can solve this equation. And up to overall SL2 translations, there is only a unique solution. Well, not unique. There is a solution. This equation is linear, so any solution can be multiplied by an overall factor. And that overall factor can be set so that we have the value of phi at the horizon. So the solution is parameterized by what the value of phi at the horizon is. And then phi diverges as we go in these directions. Phi becomes equal to plus infinity at this boundary of ADS and minus infinity in these regions. And then it has, of course, the boost symmetry around this origin, because we said that any solution has a boost symmetry, and we arrange the origin to be the fixed point of that boost symmetry. OK, in the inner horizon, phi is minus phi h. I mean, well, maybe I should give the explicit form for phi in some coordinates. So we use Rindler coordinates in this region. We have the Rindler-like coordinates, the tau square sinh square of rho plus d rho squared, for example, for the metric. That's the metric. Then phi will be phi h times cosh of this rho coordinate. So this is just the explicit solution. So now let me say a few more things about the dynamics of this action. So we had that Schwartzian action, and it had the SL2 global, the SL2 symmetries, which are gauge redundancy. So we can write down, in principle, the SL2 charges, QA, where A goes from 0, from -1, 0, and 1. So the SL2 charges can be obtained by applying the Nether method to this action with the SL2 transformations we discussed last time. So the finite form of the transformations are AT plus B over CT plus D. So we write down these charges, and it turns out that so the gauge constraint is to say that QA of the left system and the QA of the right system should be equal to 0. Okay. So here, yeah, maybe I should emphasize the following point. When we think about this problem, we can think of the dynamics just given by the dynamics of these two boundaries. And the dynamics of each of the boundaries is given by the Schwartzian action, which is local. So we have a boundary degree of freedom. So there is no propagating mode, but there is a boundary graviton, let's call it. And that boundary graviton has an action which is given by that action over there, and it's local on the two boundaries. And each of these problems has a global, at least if we write that action, it looks like a global SL2R symmetry, but that is a gauge symmetry, and we should impose this gauge constraint. And after we impose this gauge constraint, then we cannot think of these two as two independent systems. Okay? So in the unphysical Hilbert space, we can think of them as independent systems, but in the physical Hilbert space, they are connected, and we cannot. And indeed, the Hilbert space does not factorize in this approximation, as we expect. So we expect that in a full quantum gravity theory, the Hilbert space should factorize between the two sides, but it does not at this approximation. These SL2R symmetries are useful for thinking about the dynamics because these curves are, well, we can, yeah, I'm going to show you how they are useful in just a second. What?
Can you say again how you got that gauge constraint?
How I got this gauge constraint, yes. So the gauge constraint is something that we impose from the outside for this action, right? And we impose it because we want to think of equivalent as two configurations where we move the whole geometry, right? The whole boundary inside ADS2. If we do a rigid motion of the whole thing, we want to think of that as physically inequivalent, physically equivalent. And it's something that it's needed to make sense of this action that contains higher derivatives. And yeah, yes. Carry?
These charges?
Yes, yes, yes. But they are gauge charges. Yes, yeah.
The time translations, the time evolution goes downwards on the left and upwards on the right?
Well, I think we can think of the physical time as, so there is a U left here that goes up, and then, U right here that goes up, and a U left here that we can also view it as going up. And with this convention, the sum of the two charges should be 0. Okay. We have, of course, the physical time translation symmetry. And the physical time translation symmetry is related to the Hamiltonian, or the conserved charge associated to time translations for this action. And it turns out that the Hamiltonian can be expressed both as the, let's say, the right Hamiltonian as the square of these charges, or equivalently, just the Schwartzian action. Up to overall constants, I'm not keeping track of. So that's the Hamiltonian. Okay. Now let's consider the matter fields and try to understand the dynamics. Let's see. Okay. So imagine that we start. Well, maybe I'll say a few more words here. Naively, there are many solutions to this action because it's a higher derivative action and it has many solutions. But after we impose all these constraints and consider gauge equivalences, the solutions are parameterized by only two parameters. One is the value of the energy. And that is the same, due to this constraint, is the same for the h left and h right systems. And the second parameter is related to the origin of this time. So where the time equal to 0, how the two time equal to 0 points are connected. So if let's say the left time equal to 0 is here, the right time equal to 0 could be either here or here or at some other locations. And that's the second variable. And those are the two physical variables of this action. Okay. Now we'll consider systems which contain extra matter. Okay? Imagine we have some extra matter in the interior. The extra matter, we can think of the dynamics as follows. So the matter moves in an ADS2 space that is completely undeformed. Remember that we are not coupling the matter to phi or anything, so the matter moves in a perfectly ADS2 space. It therefore can be, yeah, so it is there. And there are two ways of thinking about the dynamics, one slightly more complicated and one simpler. So the slightly more complicated one would be to consider the motion of the matter and then calculate the stress tensor of the matter and then feeding it into the equation for the dilaton that I unfortunately erased. And then from there, calculate the dilaton, and then figure out from there where the boundaries are located. So the boundaries are where the dilaton acquires the value phi b, and that will determine the location of the physical boundaries. Okay? And a slightly simpler way to think about it is to think of this as three independent systems where you have the matter that will move in ADS2 and will carry some SL2 charges. So the SL2 charges are simply the eigenvalues of the states under the various SL2 transformations. They include, let's say, for example, the time translation, momentum, momentum-like spatial translation, and boost, and so on. And then we solve for the dynamics of each boundary with the action on the top right of the blackboard. And again, we'll get some, let's say, Q right charges here. And then similar, here we get for a general solution, we get some Q left charges. And then we demand that they all sum up to 0. And we allow for an overall SL2 transformation which treats as a gauge symmetry. And this determines completely the dynamics, okay, of the two boundaries. This fixes where the two boundaries are. OK, let me show you how this works in practice. So let's imagine the following. Let's start with the initial thermofield double. So this is the initial thermofield double state where the two boundaries follow in these trajectories. And then at t equal to 0, we send in some matter. Okay? Here we insert some matter that falls in. We want to understand the phenomenon of gravitational back reaction. So the fact that when we send in some matter, the horizon somehow grows, and regions that were previously causally accessible, they are not anymore. So for example, if we had a particle coming in here, we want to see what happens. And in this case, what happens is the following. As I said, there are some SL2 charges that this particle sends in, and one of them is the momentum in this direction. So let's think about this point. There is a momentum in this direction. And locally here, the charges have to be conserved because we didn't do anything to the left side. So they have to be conserved. And therefore, the momentum of this particle in, let's say, this direction has to suffer a kick that pushes it outwards. Okay? Is that clear? That should be crystal clear. No? Yes? So then it has that push. And so from now on, the boundary will not follow this original trajectory, but instead it will follow a different trajectory. So this trajectory that ends over there. Okay? And so now the new position of the horizon is not at this position, but it's at an earlier position there. Right? It's so this. I should emphasize that there is a large rescaling near the edges of this diagram. So the amount of proper time u to the boundary here is infinite. Okay. So after waiting an infinite time, all that we can see is up to here, and in particular, we cannot see this particle that was moving in this direction. Okay. Now another point is that there is a large divergence between there is an infinite a growing distance between the white line and the blue line. Okay, it's not very visible in this diagram, but these two are diverging exponentially. But that exponential divergence is difficult to see if you are just doing an experiment here. Okay, so some experiment, if you are doing observations localized within this region, they are hard to see precisely because it's difficult to distinguish a situation where we could have had the red line and the blue line, and the difference could have been that we did an overall SL2 transformation. And we have to distinguish the case where we did an overall SL2 transformation from the case where we bent this line. And the only way to measure this difference is to do some observation, which let's say either looks also at this line or looks at this and this other line. And these are more complicated observables, such as either out-of-time order observables or correlators between the two sides of the thermofield double. And with those, we can see the exponential growth. Okay. Okay, let me see what I want to say. Yeah. Okay. How are we doing with time? Are there any questions?
Would it be classical or quantum as not?
Yes. So the way I described it, it's. I described it as classical because I described the classical trajectory of this particle. But the similar things can be done quantum mechanically. I haven't discussed the quantization of this theory. We'll discuss that in a little while. I won't discuss it very explicitly. I would. Yeah. Okay. So, yes.
So you're just saying that when you put stuff in, the throat gets longer?
No, in a certain sense, it gets shorter. So let's go back to this diagram here. So I like to think of the length of the throat as the distance between this connecting region, the UV, let's say, and the position of the horizon. And when you send something in, the temperature becomes larger. And the horizon, then this moves up, and the throat becomes shorter, effectively shorter.
See, that's the confusion.
Wormhole between the two sides.
Okay. Oh, yes. Yeah, if you're thinking about the distance between these two, in some sense it's becoming longer. Yeah. Yeah, because this one here before could barely, it was very close to being visible. Now it's very far from being visible. So, yes. Right. Okay, so I think I'd like to say a few more things about the connection between this and the SYK. I mentioned the connections in terms of the symmetries. Let me say one more thing, which is the additional matter. So if in this problem, we can think of the matter in the interior and the two boundaries, and we can start looking at some interesting effects, like this one, for example. This is a very simple one. And in the SYK, we have a very similar story if we think of the analog of the matter as being the, for example, fluctuations of G and sigma in the orthogonal directions to F. So G and sigma have many different fluctuations, and there are physical modes that correspond to those orthogonal fluctuations. They correspond to conformal invariant, to leading order conformal invariant fields that propagate, that conformal invariant fields that are in SL2 representations. And so it's very tempting to think of them as propagating in the analog of these fields that propagate in ADS2. We don't have a local action for those fields in terms of ADS2, but we have a similar structure in the sense that we have an equation similar to this one that will tell us that if those fields are in some representation of SL2, then the Schwartzian variables have to adjust so that this equation should also be obeyed. So for many experiments that do not depend on the particular bulk interactions of these fields, that depend only on general properties such as their SL2 charges, we will find the same answer in SYK and gravity, precisely because of the structural similarity between the two. Are there any questions about that? And in particular, it's interesting that these SL2 symmetries that we have in the bulk, sort of allow us to move here into the interior vision. So it's a model where we are getting some glimpse into the interior. Not a very, let's say, super clear and transparent glimpse, but we are starting to get a glimpse in the sense that we are seeing explicit sort of at least symmetries that move us these particles into the interior, move the particles into the interior. This is an advantage, yeah. So there are many, and I think that's the feature of SYK that I find most interesting. That's why I try to gear these lectures to emphasize these aspects to connections to ADS2 and try to convey this feature. Unfortunately, I don't have a very clear statement and say, well, we can solve all the interior and so on. But I think that it's a feature that this model has that I think no other model has. So no other model for the interior has. Okay. Now I should emphasize that, well, I already said it, but let me say it once more. The SYK and the gravity share this boundary gravity mode. They have exactly the same dynamics for the gravity mode, but for what would be the bulk modes, the rest of the modes, they have somewhat different dynamics in the sense that the SYK seems to have, if it has a bulk action, it probably will be more non-local than any local action that you can write down on ADS2. That's the expectation, but it's something not completely understood. I will now like to spend a few more minutes explaining some aspects of the physical, a little more, expanding a little more on the dynamics of this Schwartzian action. So that hopefully the previous discussion will become more clear. So when we are at finite temperature, it's useful to think of to write f in terms of some Rindler time variable, t of u, let's say over 2. So u is the physical time, and t is something that we'll think of as the Rindler time in this diagram. And then, I mean, f is analogous to, sorry for the confusion. F is what I was calling t also here. T of u, yesterday I was calling f of u. Is analogous to the Poincaré time. So Poincaré time would be the time slices. So these are the equal row slices, or as we move time, we have this these trajectory orbits of the time, and this is describing instead such Rindler time, so other time coordinates. And then the Schwartzian of t and u, we can use the chain rule for Schwartzians to find that this is equal to the Schwartzian of the Rindler time and u plus, I guess it's minus 1/2 t prime square times the Schwartzian of tangent of this time comma t, and that's the 1/2. Okay. So that's just we apply the chain rule for the Schwartzian, and it's useful to think of small fluctuations around so the solution that I was describing here can be viewed as u times let's say 2 pi over beta. So yes.
Just re-explain what you drew there. I just didn't follow.
Yeah. When we make the discussion about the boundary terms we could put and so on, we use the Poincaré coordinates, right? The coordinates where the metric look like we used Euclidean space, but we could have used Lorentzian space. Okay. And so then solution which has t proportional to u, there will be a solution where t is just proportional to u. That will be a solution that describes this type of boundary trajectory.
That's the larger one.
Yeah, the larger one. So that's a simple solution. Of course, the same Schwartzian has some other solutions which look like this trajectory. Okay. Now, since we are focusing on solutions that look like this, we are trying to choose just from the get-go, from the beginning, a variable where the solution will look simple. The original solution we want to describe looks simple. Okay. And so, okay, we could have written this tangent and we pull it out of the hat. We don't know where the tangent appears from. But the idea is that the physical interpretation of this time is just Rindler time. Okay, so we could have done the original discussion with Rindler time as opposed to the Poincare time. And if we had done that, then we would have obtained this action by the same logic. This is a solution. It's really a one-parameter family of solutions with different temperatures. And this one-parameter family corresponds to the various temperatures we could have, various lengths of this distance between here and the horizon. And they also have different values of phi h, which are related to the temperature. I didn't derive the relationship, but if you want, we can derive it. So that's the one-parameter family of physically different solutions. So now let's consider small fluctuations around the solution by considering an epsilon of u. And we'll try to analyze what the equations of motion for epsilon are. So that's for example, necessary if you want to consider this trajectory and look at nearby trajectories. We find that this trajectory for... So we now expand the Schwartzian action to quadratic order, and we get quadratic action for epsilon, which has the form so that ft of u ends up being, well, it will be something quadratic in epsilon. So there is a term with 4 derivatives that comes from the first term over there, and then a term with okay, so we have minus 1/2 this. So, okay, so this is the action. And then we can calculate the equations of motion, and the equations of motion are very simple. The 4th derivative minus the 2nd derivative equal to 0. Okay. So what are the solutions? So solutions are epsilon. So epsilon could be a constant. So like we call it alpha 0. Then it could be could be alpha 1 times u. So these are solutions where the first contribute only to the first, and well, they are annihilated by this operator. And then there are 2 solutions which go like e to the u, and I've set here, sorry. When I went here, I have set beta equal to 2 pi. Okay, if not, beta appears in a trivial way here, so we're not going to keep track of beta. This beta is let me call it gamma. Let's say gamma plus and gamma minus e to the minus u. Okay. Okay, so that's just by simply looking at the solutions of this equation. And we can view these various solutions in the following way. So this solution alpha 1 corresponds to a rescaling of the temperature, right? So we started with the initial temperature, and now we're changing this slope, which corresponds to the rescaling of the temperature, or rescaling of the overall energy. We expect this to be certainly a physical fluctuation. Then there are these 3 constants that arise by thinking of the original solution and applying an SL2 transformation. So if you take the original solution and you apply an SL2 transformation, so one of the SL2 transformations is to change tau to tau plus a constant. That will give us this. Another is to do the other non-trivial transformations, and they will produce these other 2 terms. Okay. Okay. So the fact that these come from SL2 transformations is related to the fact that it's difficult to see these solutions if we only do local observations in time, because we are going to only look at SL2 invariant configurations. But if we had some way of seeing this growth, right? So for example, we start with one solution, like for example what we discussed here, and we are looking. So let's consider a more complicated observable where we consider, for example, a 2-point function across here the thermofield double and another 2-point function here. Then when we insert these operators, we will produce a deformation here in the contour, one of which will diverge exponentially, one of which will excite that mode. And then with the second correlator, we can detect that excitation. That's basically the out-of-time order correlator that Douglas was describing yesterday. And the important point I want to point out is that the exponent here is determined by the SL2R symmetry, the SL2R structure of this action. So that's what determines the exponent. That's why it's the maximal exponent. So you see that, So you see that this SL2R, it's an SL2R gauge symmetry. And globally, if we change everything, it doesn't contribute to anything. But by acting with operators and so on, we can excite some of these modes. And looking at more complicated observables, if you wish some Wilson lines, you get access to these growing modes whose structure is determined by the symmetries of the problem. Okay. So now a few words about the quantization of this theory. Now you look at this action. So let me write the action here. For example, in terms of the t variables, integral du. So up to a total derivative term, this action looks like t prime over t squared. So it looks very, very complicated, and you would think there is no way this could be quantized exactly. But you can, however, this problem, the quantum mechanics of this problem is exactly solvable. And as with many exactly solvable problems, there are many different ways to do it. And so I will just give you a simple way to think about it. So at least to understand the origin of the exact solvability. So the Schwartzian again has one more term that I neglected because it's a total derivative. Okay. And now we define a new variable. Let me call it rho, which is logarithm of t prime, right? And then if we define this new variable, then this term here looks like rho prime squared. So this looks like it might give us a term that looks like rho prime squared, right? At least that's the expression there. And we can enforce this equality by putting a Lagrange multiplier that looks like e to the rho minus f prime. Okay. So this action is such that if we integrate over this Lagrange multiplier, then we set rho equal to logarithm of t, and then we recover the original action. Okay. But instead, we could first integrate over f, and then we set the equation of motion for it. So we do the functional integral over f, and that sets a delta function of lambda prime. So it says that lambda prime, this integral imposes that lambda prime should be 0 everywhere, and therefore lambda is a constant, and in the end we get an action which looks like a Liouville action for rho, which is an exactly solvable potential. So it's a quantum mechanics which you can exactly solve. So that's one way to understand it. But there are many other ways that have various advantages and disadvantages. And so I will just enumerate some of the other ways, and I'll put references in the notes. So one is to look at the path integral for the Schwartzian and understand its geometric origin and understand well the measure, and then do the full functional integral by using a version of localization similar to what Atish was doing. That was done by Douglas, Stanford, and Witten. And they computed the partition function, whose result I'm going to quote in a moment. Another way is to start from the two-dimensional Liouville action and then reduce it to this Liouville quantum mechanics. That looks like an overkill because we start from a two-dimensional field theory. But the good thing is that there were many things that were understood for the two-dimensional field theory, so you can relate the two problems in a nice way. That was done by Hermann Berlinde, Turiachi, and various other people, some of you here, Mertens. And then you can also think of the motion of this particle. You can think of this as a physical particle whose action is given by the action of a particle with a constant electric field in ADS2. And that has some nice features because some other nice features. Anyway, so these are various ways to do it. And what are some of the results that have been obtained quantizing this? Before I discuss the results, I should probably say one word about when we expect that the quantum mechanics is important, right? So if we were to calculate the partition function for the theory, let's say we already saw what the classical action in SYK variables, we found that there was a classical term that went like 1 over beta j. In Reissner-Nostrom variables, the same thing would be, so just to connect the variables between the two sides, 1 over beta j would be equal to the extremal value of the radius cubed divided by g Newton. And the extremal entropy S0, which it goes like n, would be the extremal value divided by g Newton. Okay, so this is how you would relate the problems on the two sides. You can think of n as this, and then 1 over j as RE, the extremal value of the radius. So RE is equal to g Newton times the mass. Okay, so we got one obtains this, and it turns out that this is a good approximation as long as you expect, for example, that this should be good as long as the classical action is large. So for temperatures that are large enough, so this is equal to n over j times the temperature. And so for large enough temperatures, this is good, but when we go to low temperatures, we start having quantum fluctuations, and we need to do the quantum mechanics. We can, even when the temperature is large, we can compute the one-loop correction to the Schwartzian action, and doing the simple one-loop correction, which amounts to taking this action and just integrating out epsilon, right? So we do the functional integral over epsilon. It's a free theory. It's very simple to do. There is some zero-mode counting that you need to be careful about that gives some beta j to the 3/2. And so that's what you obtain perturbatively, and then you might expect further and further corrections. But it turns out that this answer is exact. So if you quantize the Schwartzian theory, this is exact within the Schwartzian theory. So now this is exact and wrong, okay? Physically wrong. In the sense that I forgot one term before I discuss that it's wrong. There is also a term here proportional to S0. So there is an e to the S0, which is the extremal entropy. So this goes like e to the n, the extremal term coming from the topological term. And this second piece comes from the exact quantization of the Schwartzian. Yes?
This quantum mechanics model has a continuous spectrum, is that right?
Yes, yes.
Is that supposed to worry us?
Yes, it should worry us. And what I'm going to show here, what I'm going to show here is a manifestation of this. So the fact that, we expect that if we took the temperature to be infinite, the beta to be infinite and the temperature to be 0, we expect here to find an integer, right? It's just the lowest energy state. But what we find instead is 0. So when beta goes to infinity, this whole partition function goes to 0. This is what I'm saying when I say that this is physically wrong. So this is not what we expect for the SYK model. It's not what we expect for black holes. But before you say, oh, I must have done something wrong, we should realize how wrong is it. So now notice that we have this huge factor in front, okay? So when beta j becomes large, let's say beta j is of order maybe of order n, so this factor is not important. That's when quantum corrections become important. So then we start getting something that starts decreasing as a power. But in order to reach to a contradiction, we really need the beta to be exponentially large in n, okay? So this is pretty good. So it's pretty good for betas which are, let's say, less than exponentially large. So that's a pretty big range of betas for which this is good. And so it makes sense to analyze this theory, and you get some nice results. And you should remember that they are not the whole answer. And of course, one would like to understand how to fix this. So what else do you need to do to fix this problem? And there is one version of this problem, slightly different version of this problem that has to do with correlators with two-point functions, which was recently analyzed in a paper by Fieldsad, Schenker, and Stanford. And they found that there are some other saddles that you need to other instantons that seem to fix this problem. So that's one thing that was analyzed. The other thing was the two-point functions. So the answer that you get in the classical theory is just 1 over sinh hyperbolic of pi t over beta to delta. And then for large Lorentzian times, there is an I here, and it's not very important. This goes like e to the minus 2 pi t over beta delta. And this is the leading quasi-normal mode that Douglas discussed. It's exponentially decreasing. And this is good as long as t times j could be much bigger than 1, but much more than n. Then this is OK. But when t times j becomes much bigger than n, then we start having some corrections. Okay? And the corrections change this behavior, and these quantum corrections. And they produce a power law instead. So very long times, the correlator does not decrease exponentially, but it decreases like 1 over t cubed. Okay. This will be correct for times which are much larger than times j, much larger than n, but much smaller than e to the s. So when we get to times of order e to the s, we need to analyze it with some techniques that go beyond the Schwartzian approximation. Okay. And this is what something very similar to this is what the paper I just quoted analyzed. And there is when you get to this regime of times is when you start seeing the eigenvalue spacing and properties of the eigenvalue spacing that become important. Okay, but there's a wide range of times where these effects are interesting. The fact that when you get very close to extremality, so you have a black hole and you get very close to extremality, quantum effects become important. So this throat cannot be viewed as completely classical. There are quantum effects that become important, but the quantum effect is just this universal degree of freedom of the graviton, right? That's what governs this, and you can take this into account by these Schwartzian methods with many different ways. So you get a little bit of insight into quantum gravity, of the quantum gravity of this very simple graviton mode. And you can start quantizing gravity in this way, and you can get results which are correct to all orders in perturbation theory. So that's the nice aspect of this problem, where the dynamics is so simple that you can quantize it, and perturbative quantization of gravity around this background does not solve the information problem. So that's one takeaway from this. You need to go beyond that. So you can get the answers, but the information problem in the form of this going to 0 and so on still remain. Okay, thank you.